after completing the fundamental concepts like vector analysis and coordinate systems, okay, and then we have completed the del and its operations. Okay, so these are the, I said these are the fundamental concepts for understanding the electrostatics and magnetostatics. Okay, now we can enter into our original concepts called electrostatics. Okay, this is the first topic of our electromagnetic field theory. So in this electrostatics, we are going to cover various concepts starting with Coulomb's law. Okay, that is a expression for the force in vector form and problems on it. Okay, then we study about electric field intensity. Okay, and the field intensity on a single charge due to a number of charges. Okay, that is another concept. Okay, next we study about various types of charge distributions. Next, we find out the electric field intensity due to infinite line charge and infinite sheet of charges. Okay, next we study about electric flux, flux density, and Gauss law and its applications. Okay, relation between E and V, all those. Next, we see about work done. Okay, from that we derive the relation between E and V. After that, Poisson's and Laplace equation, capacitance, all these concepts. Okay, energy density. Okay, these are all the concepts which we are going to study in electrostatics. Okay, so first let us try to define what is electrostatics, and next we will go to the Coulomb's law. So what is electrostatics? The term itself is saying that it is a static field. Static means stationary. That means all these electrostatics concepts, okay, in that the starting point that we have to start is a charge. Okay, so charge is either a positive charge or a negative charge. Okay, we either take a positive charge or a negative charge in this, but both charges are stationary here. We know very well that, okay, two positive charges suppose are kept nearer with each other. Okay, there is always a repulsion between them. This is what we have been studying from the childhood. But how these two positive charges, when you bring them closer, okay, how they are going to repel with each other, that we are going to see here. And suppose if you have a positive charge and a negative charge which are closer to each other, then there is a force of attraction between them. Okay, so that means two like charges always repel with each other, and two unlike charges always attract with each other. Okay, so two positive charges or two negative charges, they always repel with each other, and one positive and one negative charge will always attract with each other. So to start with the Coulomb's law, okay, we always say that, okay, 2 point charges. First of all, we have to know what is a point charge. Okay, so here I am showing you two charges. Okay, when do we call these two charges, or these two charges are point charges? Point means, okay, the point which, okay, I am representing like this, a dot, which should be very, very small, which should be very, very small on that very small surface, which is like a cylindrical structure. If in that, on that cylindrical structure of surface, if we distribute charge, and that charge we call it as a point charge. So point charge is the charge which is distributed on an infinitely small volumical surface. Point charge is a charge which is distributed on infinitely small volumical surface. Infinitely small means very, 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 very small. Okay, that very, very small volumical surface, I am calling it as volumical surface, means that surface should be like a very small spherical, inside it is empty. So automatically that outside we will be having some surface. On that surface, if you distribute some positive or negative charge, we call it as point charge. So in Coulomb's law, we are always going to discuss about 2 point charges or 3 point charges or n number of point charges. So that point charge means, okay, that. Okay, this is one of the types of charge distribution. Okay, so we have 4 different types of charge distribution: point charge, surface charge, line charge, and volume charge. Okay, so this is the first type of charge distribution, that is called point charge distribution. Okay, so after completing this point charge distribution, let us now define what is electrostatics. Electrostatics is a study. It's a study of something. What is this? What is that we are going to study? It's a study of the force exerted by some system of charges. System of charges means, suppose there are n number of positive charges or n number of negative charges which are kept closer or which are kept at one location. Okay, let us say this is the place where some n number of charges are kept there, that we call it as system of charges. So that means all these charges, every charge will have some field around it. So all these charges are going to form a very big or very huge amount of electrostatic field. Okay, so all these charges, suppose if you bring another positive charge or negative charge which is closer to that, definitely these charges are going to exert some force on it. That means these charges will push that charge away from it, because these are huge amount of positive charge and this is a very little amount of positive charge. Obviously, this will exert some force on that positive charge, and that study of force exerted by the system of charges on that single charge is called as electrostatic field. So electrostatics means it is a force, it's a study of the force exerted by the system of charges on a single charge is called as electrostatics. Then what is electrostatic field? Electrostatic field means it is a field around a positive charge or field around a negative charge, is simply called as electrostatic field. The condition here is that charges should be stationary charges. If the charges are moving, then we cannot get electrostatic field. All the charges, whether they're positive or negative, should be stationary charges. Then only the field around that positive or either positive or negative charge will always give us electrostatic field. Okay, this is what the first thing that we are going to see in electrostatics. Okay, so next the topic that we are going to start in this electrostatics is the Coulomb's law. So every electrostatics concept starting with Coulomb's law. What this Coulomb's law says? Who is this Coulomb? Okay, Charles Coulomb. Okay, is the one who gave us there is a force of attraction or there is a force of repulsion between any two charges, whether the two are positive or negative, or one is positive and other is negative. Okay, so if there are two charges which are kept closer with each other, there is always some force of attraction or force of repulsion between them, and he calculated that force of attraction or repulsion by taking two balloons which are hanged in a vacuum room, and that balloons are charged with some positive or negative charges, and he calculated the force of attraction or repulsion by using some devices, and then he finally concluded one statement. Okay, that statement here we are going to see here. So let us now take a positive charge as the point charge. The point charge just now I have defined. So this is one positive charge and this is either another positive or negative charge. Okay, these two positive charges are represented by, so this is plus Q1 or simply Q1 because it is already positive charge, and this is let's say Q2, which is also another positive charge, and these two charges are separated by some distance d. These two charges are separated by some distance d, and these charges you just join them with a line. These two charges you just join them with a line that is like this. This is the line joining of the 2 point charges. Okay, so and the separation distance is d. Okay, then this Coulomb's law states that the force of attraction or repulsion between the 2 point charges here, because the 2 point charges are positive charges, there is always force of repulsion between them. If one is positive and one is negative, there is a force of attraction between them. So that force of attraction or repulsion between the two positive 2 point charges is directly proportional to the product of their charges, that is Q1 into Q2, and inversely proportional with the square of the distance between them. Let us call this distance is r. Okay, so that is F is inversely proportional to square of this distance square. And also the third statement is very, very important for us. The force always acts along the line joining the 2 point charges. That means this force will always act along this line joining. This line joining is, okay, so this Q1, Q2 when you join, so if this exert force on this will be moving only in this line direction. This is exerting force on this, then this Q1 will be moving in the same line. That is what is the meaning of the third statement. So the statement of Coulomb's law is, it is the force of attraction or repulsion between the 2 point charges is directly proportional to product of their charges and inversely proportional to square of the distance between them, and the force always acts along the line joining the 2 point charges. This is expressed in mathematical way as F is directly proportional to Q1, Q2. This is the first statement of Coulomb's law. And F is also inversely proportional to square of the distance between them. Okay, and the third is force always acts along the line joining the point charges. That is going to get in vector form of Coulomb's law. Okay, so if you combine or if you join these two, then we are going to get F is directly proportional to Q1, Q2 by R square. Q1, Q2 by R square. But if we observe this, okay, so if you remove this proportionality, you will get a constant, but this F is always expressed in newtons. Newtons means kg meter per second square. Okay, F equal to m into A. M is kg and A is acceleration meter per second square. But if you observe this, the units of charge is coulombs, and this is also coulombs, and this is distance is expressed in meters. So coulomb square per meter square will never be equal to the kg meter per second square, which is the unit of Newton. That's the reason we have to take a constant k, which is going to compensate the units of this coulomb square per meter square and will give us the units of newtons. Okay, for that purpose, we take a constant of proportionality, which is k. Okay, so equal to k into q1, q2 by r square, and this k is called as constant of proportionality, or we can also call it as Coulomb's constant. This is also called Coulomb's constant. And this Coulomb's constant or constant of proportionality is equal to 1 by 4 pi epsilon into q1 q2 by r square. Into q1 q2 by r square is the expression for the force. But how this epsilon is going to compensate the units of it? Or this entire k units will be what? The k units will be here equivalent to, it is, we are putting it in numerator, so it is newtons into meter square per coulomb square. The units of this is k is Newton meter square per coulomb square. So here this is coulomb square per meter square. So multiplied by this, okay, this k into that q1 q2 by r square will be coulomb square per meter square. So this meter square, coulomb square getting cancelled. It is getting remained as Newton. So k into q1 q2 by r square is force. So we are getting the units as newtons. Okay, so in this way, k units will be taken as Newton meter square per coulomb square. That is a unit of k, and that is equivalent to 1 by 4 pi epsilon naughts. So epsilon, so 4 pi is a constant, and epsilon will be called as permittivity of medium. This is called permittivity of medium. So this epsilon will be equivalent to epsilon naught into epsilon r, and this epsilon naught is called as permittivity of free space, and epsilon r is called relative permittivity. It is called as relative permittivity. So epsilon is permittivity of a medium, and epsilon naught is permittivity of free space, and epsilon r is called relative permittivity. So epsilon will be having the units of farad per meter, and epsilon naught is having a value, okay, which is also expressed in farad per meter. It is equal to 8.854 into 10 power minus 12 farad per meter, or this is also expressed as 1 by 36 pi into 10 to the power of 9 farad per meter. So this and that both are, okay, similar values. Okay, from this 1 by 36 pi into 10 to the power of 9 itself, we have got 8.854 into 10 to the power of minus 12 farad per meter. Sometimes we use that, or sometimes we use this. Both are expressed in farad per meter, and epsilon is also expressed in farad per meter. So we can get, so epsilon R will be equivalent to epsilon by epsilon naught. So relative permittivity is equal to permittivity of medium by permittivity of free space. So farad per meter by farad per meter, so it will be getting cancelled. So relative permittivity will not have any units. Based on the material value, material type of the material, the relative permittivity is going to vary, because this is fixed and this is going to vary based on that epsilon is greater than or lesser than the value of epsilon naught. Okay, then we are going to get epsilon R value. Okay, epsilon is equal to, suppose epsilon naught, then epsilon R will be 1. So that is for generally free space or vacuum. So for a vacuum, epsilon will be equal to epsilon naught. That means relative permittivity of that, okay, vacuum or free space will be equivalent to 1. Okay, so the Coulomb's law always states that 1 by 4 pi epsilon into Q1 Q2 by R square, and it is always expressed in newtons. It is always expressed in newtons. Okay, this is simply the magnitude of this force, okay, which is expressed here. Okay, but if we want to find out its direction also, that means force exerted by Q1 on Q2 and Q2 on Q1, how we can able to measure that? Okay, that also we are going to see here. So this epsilon, we can write it as epsilon equal to epsilon naught into epsilon R here. Okay, that is going to give us the final expression for the Coulomb's law. But in free space, this will become F equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. So that is further going to be simplified as, so in free space, what is going to happen is epsilon will be equal to epsilon naught, or we can say epsilon R equal to 1, relative permittivity equal to 1, then the force will be equivalent to 1 by 4 pi epsilon naught into Q1 Q2 by R square newtons. This epsilon naught is expressed as 1 by 36 pi into 10 to the power of 9. So if you substitute that here, 1 by 4 pi into this epsilon naught is 1 by 36 pi into 10 to the power of 9 into Q1 Q2 by R square here. So this goes 9 times. Okay, then this can be further simplified as, this is 9 into, if it goes up, 10 to the power of 9 into Q1 Q2 by R square. Okay, this is the force expression. Suppose, for example, if the two charges Q1 and Q2 are equal to 1 coulomb, and this is also 1 coulomb, and this R equal to 1 meter, that means if this is plus 1 and plus 1 coulombs, okay, this is going to become 1 into 1, and this is distance between them, suppose is 1 meter, then the force of repulsion between those 2 point charges, that is 1 coulomb and 1 coulomb charge, will be 9 into 10 to the power of 9 newtons. That means it is almost equal to 900 crores newtons. That means very huge amount of force of repulsion between those two charges, even though it looks like 1 coulomb and 1 coulomb of charge, which is very, very smaller. But 1 coulomb and 1 coulomb charge is not smaller. There are huge amount of charges. Okay, so there is a very huge amount of force of repulsion between them. Okay, so based on, by seeing the charges, we cannot expect how much amount of force between them. So we always need to calculate the amount of force, okay, between the 2 point charges. Okay, this is the way we can calculate the magnitude of the Coulomb's law. Now we also try to see how can we find the vector form of Coulomb's law? Okay, so that is